we want to essentially provide performance. So in addition to the score above, we want the area under the ROC curve, but also we would like a visual representation of it.
We're going to enhance our CardioROC game by calculating the area under the curve, AUC, for the ROC plot. The AUC gives us a more meaningful metric for evaluating performance. It represents the overall ability of the player to correctly identify abnormal versus normal ECG waveforms. A higher AUC means better accuracy. To do this, we'll use a method called the Trapezoidal rule to estimate the area under the ROC curve. This involves summing up the small areas under the curve, approximating them as trapezoids between consecutive points. Next, we'll visually represent this AUC on the ROC plot by shading the area under the curve. We'll fill the space between the ROC line and the x-axis with a light color, making it easy to see how much of the graph is covered by the curve. Finally, we'll display the AUC value next to the current score, giving you both a numerical and visual way to track performance. As you interact with the game, you'll see the shaded area change, reflecting how well you're doing in distinguishing between normal and abnormal heartbeats. This will help make the game more interactive and informative, giving instant feedback on your diagnostic skills. Let's dive into implementing these features and see how they look.
It seems to be calculating the area okay. The area under the curve is normally calculated from the 0, 0 to 1, 1 line or not. That's 0 to 5. Okay, if we don't click on it, we should get another green. 0 to 5, 8. As it was working. So the area under the ROC is calculated, I think, correctly. We need to make sure it's actually calculated from the horizontal, the baseline, the 0, 0 to 1, 1. What's that line called? Yeah, the chance line. Yeah, we have the chance line. So to calculate the trapezoidal integration is always computed from the x-axis up to the ROC curve, not from the baseline. The area under the curve, I assume it's calculated correctly at the moment, but we're still testing that. 252, 253 should have a green. Still 0, 0. Okay, we're going up. Yet the area under the curve cannot be calculated yet. That should be going a bit faster. Okay, so we are not clicking on that. We'll click on this one just so we essentially can have the calculation. Okay, where's the calculation? Okay, so a green, we just go for red. Yep, and we go for now red. Yep, 0.25 is area under the ROC curve. 0.25 should have now green. 0.29 should have now green. 0.299. Okay, so that's working okay. If we don't click on this one, we should have 0.3, 0.323, 0.324. So it's going up. That's good. Getting green, meaning correct responses. 0.325. Okay, so if we click on it, we get 0.325. Now 0.34. So if we don't click on it, 0.348. It's not very sensitive. 0.371, 0.373, 74, 75, 76. Yeah, there is a bit of a funny thing about it. Oops. Okay, so it seemed to work well, kind of. 383. It's becoming harder because it's faster every 50 points. What happens if we just keep clicking on everything? 382, Yeah, the funny thing about it, yeah, that's a bit counterintuitive, isn't it? The fact that, yeah, maybe someone can explain, or the robot can explain why. How does it make sense when, if we just keep clicking on everything, the false positive, so we're going right on the false positive rate, but the score, the area under the curve is increasing. The score would be, you know, better. I'm having difficulties to explain it, but something doesn't seem right. Should there, yeah, now for example, if we get another 395, 397, 4, so we're getting wrong responses. 560, 570, 580, 590, 600, 590. Yes, so the score is behaving correctly, but yeah, we might need some sort of adjustment to this, because yeah, essentially what's going on is that if we have a normal ECG waveform that we should not have clicked on, but we did, the score is going down as expected, but the area under the curve is still going up. But in theory, it should be going down, because, correct me if I'm wrong, but higher area under the curve means higher performance. So it should not go higher for incorrect responses, should it?
What you're observing is due to how the area under the curve, AUC, is calculated. The AUC measures the model's ability to distinguish between classes. It doesn't directly decrease for every wrong click. When you click on every waveform, whether normal or abnormal, you are increasing both the true positive rate, TPR, and the false positive rate, FPR, simultaneously. Since the AUC is derived from both the TPR and FPR, clicking on everything can still increase the AUC because both rates are moving upward. Ideally, correct identification should increase TPR more than FPR, but since you're clicking indiscriminately, you see an increase in both. This leads to the AUC going up even though performance is not actually improving. To address this, you might want to penalize incorrect clicks more heavily, or implement a different strategy for updating the AUC based on the balance between true and false positives.
We can solve it somehow by making sure that the interpolation is always going through 0, 0, and also 1, 1 points on the ROC curve chart.
Yes, ensuring the interpolation always passes through the points 0, 0 and 1, 1 on the ROC curve will provide a better representation of performance and prevent misleading AUC increases. To implement this, 1. Add points 0 and 1, 1 to the ROC points array before sorting, ensuring the curve starts at 0, 0 and ends at 1, 1. 2. Modify the AUC calculation to always consider these two fixed points. This forces the ROC curve to show an accurate trade-off between the true positive rate and false positive rate, making the AUC less likely to increase with indiscriminate clicking. Here's a brief code modification. JavaScript function update ROC, ROCpoints.push, TPR 0, FPR 0, correct true. Add 0, 0, ROCpoints.push, TPR 1, FPR 1, correct true. Add 1, 1, ROCpoints.sort AB equals A.FPR best B to FPR. Draw ROC. This ensures the curve correctly reflects performance, always starting from 0, 0 and ending at 1, 1, representing both extreme cases where nothing is detected and where everything is detected correctly.
Differences when changing the initial conditions. So what happens if we comment out those initial conditions, so we do not assume that the curve is going through 0, 0 and 1, 1? what effect would that have? We can make an assumption, but just let the robot do its thing. Why misleading? Doesn't it just mean that we are making less assumptions or not making any assumptions, and that the area under the curve will start from 0, or it won't be able to actually calculate it?
By commenting out the lines that ensure the ROC curve passes through 0, 0, and 1.1, you're removing the assumption that the curve always starts and ends at these points. This means, 1, the AUC will still be calculated, but it may not represent the full range of performance from no positive classifications, 0, 0, to all correct positive classifications, 1, 1. 2. The area under the curve might start at the first actual data point added instead of 0, 0, and may end at the last point added, which can make the AUC less comparable to a standard ROC curve. Effectively, you're allowing the data itself to define the curve, which could be more representative of actual performance, but less standardized for comparison.
Okay, instead of actually pushing the data points into the curve, can we just assume that the interpolation line is going through 0, 0 and 1, 1 all the time, but don't actually add those points to the chart?
Yes, you can assume that the interpolation line always passes through 0, 0 and 1, 1 without actually adding those points to the data. This can be done by modifying the drawing logic to explicitly draw lines from 0, 0 to the first point and from the last point to 1, 1. Adjusted code to ensure the curve passes through 0, 0 and 1, 1. 1. Modify the DrawROC function. JavaScript function DrawROC. ROCCTX.clearRect 0, 0, ROCCanvas.width, ROCCanvas.height, DrawROC reference line.
Okay, I'm still testing this code, but there is one thing that might be a problem. There is an assumption of a data point before I actually click on anything. And that data point remains there after the click. Do you know what I'm talking about? Can you explain that bit?
Yes, I understand the potential problem you're referring to. When the game starts, there are no clicks or decisions made, yet there may be an initial ROC data point that gets plotted, likely at 0, 0, or remains on the chart after the first click. This initial data point represents the starting condition where there are no true positives, true negatives, or false negatives, essentially no performance data yet. After your first click, this initial data point might still be affecting the curve because it has been added to the ROC points array, even though it doesn't correspond to any real game action. How to fix this? To avoid this, you can initialize the curve correctly and ensure no extra points are added at the start. Instead of adding a data point at the beginning, only start adding points to ROC points after the player has made an actual decision. Adjust the updateROC function as follows to prevent the initial assumption. JavaScript function updateROC, const tpr fpr correct equals calculate ROC points, / only add points after a decision has been made if hits plus misses, false alarms plus correct rejections 0. ROC points.push tpr fpr correct. This ensures that no points are added to the ROC curve until the player has interacted with the game.
Okay, the other question is how many points, data points do we need, like the minimum number of data points before we can actually make a performance metric calculation?
To calculate a reliable performance metric like the area under the curve, AUC, for the ROC curve, you generally need a minimum number of data points to represent different states of the classification task. At least 3 points are necessary for a basic interpolation. 1. A point near the origin, 0, 0, representing a state where there are no false positives or true positives. 2. A middle point that reflects the actual performance data, like true positives and false positives. 3. A point near 1, 1, showing the end state where all instances are classified. However, more points, 10 or more, will give a more accurate and smoother ROC curve and AUC, providing a better estimate of the model's performance.
Should we ignore the first couple of data points before we actually making area under the curve calculation? Also, should we ignore, should it start, in the beginning, should it be 0.5 or should it be normalized to 0? I mean, the calculation, the initial calculation. So essentially we're trying to cover the edge cases for this calculation. Also currently, for example, we have 0, 1 data point. That doesn't seem to be very realistic. It's just skewing the performance calculation. Also, how do we go about the points that are below the 0, 0, 1, 1 line?
Handling initial data points and adjusting the AUC calculation. To improve the AUC calculation and handle the initial points correctly, 1. Ignore the first few data points. At the start, there might be a lack of sufficient data to represent performance accurately. You could introduce a minimum threshold, e.g., wait until at least 3 or 4 points are available before calculating the AUC. 2. Normalize the initial AUC value. The initial AUC should ideally start around 0.5, which represents random guessing. To achieve this, ensure your curve begins at 0, 0 and ends at 1, 1, but does not artificially push any data points there. 3. Handling points below the diagonal line. Points below the diagonal line, the chance line from 0 to 111, indicate worse than random performance. These should be included as they provide a valid representation of performance. However, they should lower the AUC, which will reflect poor performance. Implementation steps. Filter initial data points. Add a check before calculating AUC to ignore the first few points until enough data is collected. Ensure the baseline AUC starts at 0.5. Before user actions, initialize the ROC plot without assuming performance above chance. Account for points below the diagonal. Retain points below the diagonal line as they provide an accurate measure of performance, and let the AUC naturally reflect their effect. Looking at the updated ROC curve, we can refine the performance metric calculation by considering the initial data points more carefully. 1. Ignore the very first data points. Start calculating the AUC only after a few meaningful interactions, e.g., 3 or more points. This avoids skewed results from initial guesses or non-representative data. 2. Normalize the AUC value. Ensure that the calculation reflects random performance, 0.5, until enough data is gathered. 3. Handle points below the diagonal line. These points represent worse than random performance. Keep them in the AUC calculation, allowing the metric to reflect true performance, whether good or bad. This will help in properly adjusting the AUC downward when performance is below chance.
Okay, so when ignoring the first data points, should we just start calculating the performance when we have one of each? So one false positive, one false negative, one true positive, one true negative. How does this sound as a minimum condition for starting calculating performance? Are you suggesting for the second point that in the beginning a random performance should be indicated or no performance at all? So should we start with 0.5 or start by like a text line saying not enough data points to calculate performance? Now with the third point, with handling points below the diagonal line, yes, those represent worse than random performance, but they do not seem to affect the AUC calculation at the moment.
We should wait until we have at least one of each type of outcome. One false positive, one false negative, one true positive, and one true negative. This ensures we have enough data to truly reflect the player's performance. Instead of starting with an AUC of 0.5 or random guessing, let's display a message like not enough data points to calculate performance until the minimum conditions are met. This keeps things clearer. Points below the diagonal are indeed worse than random. We should make sure they impact the AUC negatively. If they currently don't, check your calculation method. These points should pull the AUC down.
So does this mean we are not starting off the area under the curve of 0.5? Should we just have a string instead saying that there's not enough data to calculate the performance? Okay, we need to check if the area under the curve is calculated correctly. I'm just looking at some of these example images. It looks a bit odd.
Looking at the images, the area under the curve AUC values do seem a bit off given the distribution of points on the ROC curve. To ensure the AUC is calculated correctly, check that. 1. Trapezoidal rule calculation. Ensure you are properly implementing the trapezoidal rule when computing the AUC. This means that for each segment between two ROC points, the area is calculated correctly using x2 minus x1 to y1 plus y2 per 2. 2. Ordering of points. Verify that the ROC points are correctly sorted by false positive rate, FPR, before performing the area calculation, as this is crucial for calculating the AUC accurately. 3. Correct bounds. Make sure the curve always starts at 0, 0 and ends at 1.1 without artificially adding points. If those points are missing, the AUC could be underestimated or skewed. If any of these steps are not correctly implemented, the AUC may not reflect the true performance of the classifier as shown by the ROC curve.
Is it possible that the problem was because we had a negative score, so all the data points were below the chance reference line? Now that they're above the chance reference line, does this look correct?
Yes, it is possible that having all the data points below the chance reference line was causing the AUC calculation to appear incorrect. When points are below the diagonal line, 0, 0 to 1.1, they indicate performance that is worse than random guessing. Now that some points are above the chance line, the AUC appears to be calculating more appropriately, reflecting a better diagnostic performance. A negative score means more incorrect than correct decisions, which might align with having data points below the chance line, while a positive score with points above the chance line indicates better performance. The area under the curve, AUC, is low in your current game state because the majority of the data points are clustered near the bottom of the ROC curve. This indicates a high false positive rate with a relatively low true positive rate. When the ROC points are concentrated along the diagonal line or lower, it suggests that the performance is close to random guessing. If most of your actions result in incorrect classifications, or if correct classifications are not improving the true positive rate significantly, the AUC will reflect that with a lower value, demonstrating poor diagnostic performance. Improving the AUC would require making more correct decisions, correctly identifying abnormal or normal waveforms, and reducing false positives and false negatives. In other words, you need to move more of the points towards the top left corner of the ROC curve, where the true positive rate is high and the false positive rate is low.
Okay, we'll continue this next time. We're still testing it. You can also test it yourself as well. It's already available on the website. Yeah, go check out the website. And I'll see you next time. Bye.